Hello there, folks. Welcome to another exciting edition of HL Chemistry Flipped Classroom. This is Mr. Los. Welcome. I hope you're doing okay. We are going to be talking about some graphical stuff today. Now, this is stuff that in theory, you might be able to do and figure out, but I've found that students often find it pretty challenging. I've posted a selection of practice questions that are linked to in Schoology that are going to be the questions that I'm going to use when I go over this. So you'll definitely want to have that handy. If you can print it out, great. If not, hopefully you have some way to reference it. Okay, so in these questions, what we need to do is think really carefully about what the information is being presented, what we're being asked to graph. By the way, when you see the word sketch in the IB circles, what that means is it doesn't necessarily need to be quantitative, but we should probably have the axes labeled and things like that, and it's just more about the general shape. Okay, so suppose the reaction begins with identical amounts of CO and O2. No CO2 is present initially. Sketch a concentrations versus time graph for all reactants and products, assuming the reaction does not go to completion. So let's just start there, and we'll worry about B later. Okay, so we're just going to make some axes here, so we'll just label them generally concentration versus time. Now, it doesn't really give us a time unit. Concentration is going to be mole per cubic decimeter. Okay, so the first thing we have to remember is that the concentration of the reactants is going to go down and the concentration of the products is going to go up. And the amounts of CO and O2 are identical. So one thing we would want to think about here is that the mole ratio is 2 to 1. And so keep in mind that the rates, therefore, are going to be different. CO2 is going to be consumed at twice the rate that O2 is going to be consumed. So the concentration of both these are going down because they're reactants, and the concentration of CO2 is going up. So that's kind of what we're going to look at. It's not going to go down in a linear fashion. It's going to go more in a curved fashion because remember the rate's not constant. The rate's going to start faster and go down. And so it might look a little something like this. Okay, so if this is the O2... Oh, by the way, what not go to completion means is by the time they stop, this reaction is still going. So like the concentration of CO and O2 are not necessarily going to go to 0. So let's just start and let's make one, maybe something like that. So let's call that our O2 graph. And then what should be different about our CO2 graph is it should be, in theory, it would be twice as steep as any given point. Now, that's obviously going to be a little bit difficult to actually do, but we're just going to kind of do our best with it. But it's steeper because of the 2 to 1 ratio. Also, twice as many moles end up getting consumed. And again, maybe I haven't quite scaled that properly. There should probably be a bigger difference between them. But I think in terms of the general shape, we're looking okay here. And then, so all reactants and products, so then we have to graph the CO2. Now, the CO2 concentration is going to start at 0 and it's going to rise up. Its slope should be similar to the CO slope except negative, and it might look a little something like that. Now, it wouldn't necessarily cross over these other ones and be at a greater concentration, but I think in general, given the information that we provided in A, this is kind of what we're looking at here. So for B, it says sketch the graph that would result if the reaction was repeated at a higher temperature. Okay, well, let's just kind of make that one right next to this one. And we've got concentration, we've got time again. So what's that's going to change is the rate. It's going to make everything faster. So the way it would look different is maybe something more like that. I'm going to do a better job of, there's my CO, there's my O2, and then there's my CO2. So rather than, the time, I guess, when the reaction is going to dramatically slow down is going to be a lot sooner. And again, I don't think I've sketched these perfectly in proportion, but I think that something like this is pretty reasonable. Okay, so that's the first question there. Here's the second question. And I know I went over that kind of fast, guys. Obviously, feel free to go back and take a look. So I want you guys to think about this for a second. This can be very tricky. Really think about the information you're being given here, the the concentrations and everything. All that is important on how this ends up looking. So we're going to be making 3 graphs in the same axes. I'm going to suggest that I'd like you to at least try A and get experiments 1 and 2 graphed, and pause the video for a moment, and then we can talk about that a little bit, and then we can look at 3. Okay, so we've got hydrogen peroxide decomposing here into water and oxygen, and we've got 100 cubic centimeters of 1 molar H2O2. So basically, we're sketching volume of oxygen versus time. We're going to sketch them on the same axes. So it doesn't say necessarily what volume unit we're going to be using, probably cubic centimeters, but that's fine. And time here, and again, not necessarily having the time unit, but no big deal. Okay, so the volume of O2 is going to be going up, not in a linear fashion. Slope is the rate here again. So let's just draw the first one, and it doesn't matter a ton where exactly we put it, but let's put it something like this. Now we're assuming all the hydrogen peroxide decomposes, so eventually the volume of oxygen is going to level off. So let's call that experiment 1 right there. I'm going to change colors to do experiment 2 just to make it a little more clear. So 100 cubic centimeters of 1 molar H2O2. Now one thing that some of us are still making mistakes on is how we would find moles here. You don't actually need to calculate the moles, but just for kicks, remember that when you have a concentration, you always want to use not the molar mass of H2O2, but change that concentration into a conversion factor. So this is in fact going to be 0.1 mole of H2O2. If you find yourself using molar masses when you're finding the moles of a solution, you're doing it wrong. We need to use the volume and we need to use the concentration. So in the second experiment, what's changing is we're using half the volume, but we're using double the concentration. Now maybe you can kind of do in your head and realize that we're actually going to end up getting the same amount. The number of moles is going to be the same. That's a 0. It's 0.1 moles in both cases. Sorry, that decimal should be there. So because the volume is half but the concentration is double, the moles are the same. They're 0.1 in both cases. So what this means is we're going to make the same quantity of oxygen but just faster. So what we should have done with this graph is shown it steeper because it's faster, but then level off, and I messed up that a little bit, level off to the same point. So IB loves to ask questions like this, by the way, and they would definitely be if you didn't have experiment 2 leveling off at the same point, they would definitely count that wrong. Okay, so all that said, if you didn't do B yet, and maybe you messed up A, but with your newfound knowledge, maybe you could take a second and pause it and do experiment 3 before we go any further. Okay. So let's take a look at experiment 3. I'll do this in green, and it says at experiment 3 of the graph, this time 100 cubic centimeters of 2 molar H2O2 is used. I'm going to have to see if I can move this down. Experiment 3, now that I fixed my axes here, 100 cubic centimeters of 2 molar, so that was the concentration that's in experiment 2, except there's twice the volume, so we're going to be making twice as much stuff. It's going to go up at about the same clip here as number 2. It is going to take a little bit longer because there is more stuff to react. And the bottom line, though, is we're going to end up making twice as much stuff as we did in experiment 1. Now, I maybe have made a little bit too much here. Looks like a little more than double. For a sketched graph, this would be fine. If you had to make if IB gave you like an actual scaled graph and they said like plotted or something like that, they would really be expecting literally 3 to be twice as 1, and they would check that. Okay, so, and I recognize the challenge of this, guys. Go back and take another look if you're having a little bit of trouble, or email me, ask me questions. But what I'd like you to do is take a look at this one here, and I'm just going to have you pause it, and then I will I'll sketch these out, and we'll kind of run through it so you can see how you were doing. Okay, welcome back here. Something that's important to notice here is that the HCl is in excess. which means that the calcium carbonate is what's governing how much stuff that we end up making. So volume versus CO2 versus time, that's A. That's just kind of our standard increase, but not in a linear fashion, and probably leveling off. It doesn't necessarily say that, but that's fine. Crush it into a fine powder. That's going to increase the rate of reaction. It's going to increase the surface area, so it's going to go faster. But we are going to end up making the same amount of stuff because the HCl is in excess. Again, the CaCO3 is governing it, so we're going to end up making the same amount. So we should have something that's starting off at a faster slope, but leveling out eventually at the same place. Sketch the graph that result. The experiment was repeated with twice the mass of chalk. So it seems like they're talking about the one where it's not crushed into a fine powder. So the rate would be similar to A. It might be a little faster. I didn't do a great job. It might be a little faster though, because there actually would be more surface area if there was just straight up more chalk in there. So it might be going a little faster, but it's definitely going to end up making twice as much as A did before, if the experiment was a completion. Now, if HCl is not in excess, none of this stuff is necessarily true. So that's why that statement has to be in there. If the HCl would end up becoming limiting, then there would be a different story here, and the graphs wouldn't necessarily look like this. So here's one more. It's the same type of thing, and just another type of graph, this time just one quick graph, and then see if you can figure out this calculation. So pause it, take a look at it, and then I'll go through. Okay, so this time it's mass of the container versus time. Now if you think about it, the CO2 is going to leave the flask, so the mass is going to go down over time. But still, not in a linear fashion. Basically the mass loss here is the rate. And so you should have something that maybe looks a little bit like this. The mass of the chalk piece was 2.50. It stopped after 185 seconds. Calculate the average rate of the reaction in mole per second. Okay, so we got a mole. We got to make that unit happen. It's going to be moles divided by seconds. So it mentions in the other problem, or from looking at the chemical reaction, we can realize that chalk is calcium carbonate. Calcium carbonate's molar mass is very close to 100. So we can change the 2.50 grams to moles. It's about that many moles. Call it 0.250. 3 sig figs is probably about right. And then we just need to divide that by the number of seconds that the reaction took place in. And so we've got moles divided by seconds. We've got the right unit. More than likely, that means we're doing the right math. At least we've done the correct mathematical operation somewhere along the line. And so, yeah, there we have it. That's the molar mass. So there's more practice with this in your workbook. Email me, ask me questions. Come to the office hours. Whatever you need to do to help yourself out. Stay safe out there, and hope to see you again soon.